Okay, we have only 5 remaining lectures, and fortunately, we have covered most of lecture contents in our last semester. So I'm quite happy to cover the mandatory coverage. So now let's go to the more advanced topics in this course. Uh, First, in the second in the first half of this lecture, today's lecture, I will briefly cover some remaining features of this course. After that, I will move to the next one. In the last lecture, so lecture 19, not 20, so we have discussed about the, let's say, let's go to directly to lecture 19 material. So at the end of our previous lecture 19, so we have covered this hot carrier effect. So when we apply certain high bias, in this case maybe the voltage was almost 2.5 volt. When we apply such a high voltage, then some of our electrons, very few of them, can be quite energetic. So they can have quite a high kinetic energy, and that can introduce something called as a hot carrier effect. So they are called hot electrons, and they can produce a pair of secondary electrons. So this guy is hot. Hot means that it has high kinetic energy, and when it has high kinetic energy, it contributes some of its kinetic energy. For example, like just amount of band gap energy is transferred to the electron previously occupying the valence band, and now it is moved into this new conduction band electron. So this one is secondary electron, and this one is a secondary hole, and these secondary electrons and holes are splitted because electrons are attracted to this drain, and holes are attracted to this substrate. So we can expect quite a high substrate current, which is almost comparable to that of drain current. So here we have certain differences. Of course, this drain current is much higher than substrate current. It means that this difference comes from the conduction from source to drain. This is a major component, but this substrate current is originated from the amount of electron hole generated by this hot electron. So now we will continue our discussion about this hot carrier effect. Then I told you that some of those electrons become hot. So how often our electrons can be hot? So that is the question of our practical interest. So that is well described by this energy distribution function shown here. So this is the function f. So it can be regarded as a kind of a probabilistic density, so which is within the range of 0 to 1. So yes, sometimes it overcome this one, but for a while just forget about it. So if this is close to 0, then there is almost no electron occupying that energetic state at a certain position, and if it becomes 1 or close to 1, then that energy state is almost completely occupied. Then maybe you can ask me this question. So we know the Fermi-Dirac distribution. So Fermi-Dirac distribution, and always we just wrote that function as a function of electron, so energy only. So have you ever had any dependencies on position? So usually not. So, but please note that this Fermi-Dirac distribution is just equilibrium property. At equilibrium, we don't have any dependency on our energy distribution on this real space position. Everywhere we have the same energetic distribution, but right now we are considering such kind of a non-equilibrium case. Now we have a non-zero drain bias, so drain current is not zero. In this case, it is impossible for us to define a certain equilibrium distribution. So we have to generalize it, and point-wise, we have a dependency of our electron distribution. So let's have a look at this right figure. So you can see that here, this function. Here, this is corresponding to the position. This is more close to our source. For example, please, this is not exactly obtained from our MOSFET, but we can make a good analogy about it. So it starts from source and it ends at drain. And now you can see that its energy state starts from certain amount of energy here. So this is energy scale, and beyond that energy we have a distribution function called F here. And now you have different bottom energy shown here in drain part. What is it? We are currently looking at certain graph like this. So maybe you are quite much familiar with this kind of diagram. So here we have a position, and if we just draw energy, then we draw minimum conduction band position as a function of x, then we may have this red colored line. Then where can you find this red colored line? This red colored line is corresponding to this red colored line. Here you can have this red colored line, and beyond this energy, maybe we have some chances to fill our empty space with electrons. And if we ask ourselves how probable we fill this state and how probable we fill that state, so you may understand there is a higher probability to fill these states than states in this high energetic range. So exactly the same information can be obtained by this distribution function. So for example, here we have a certain position whose value is I don't know what the value exactly is, but let's say that just about 10 to the minus 5, for example. It means that any state at this source side and the energy corresponding to energy value, in this case 0 electron volts, there is a probability of occupancy just about 10 to the minus 5. Only 10 among 1 million electrons have a certain probability to occupy this state. So this is the physical interpretation of electron distribution function. So it is position dependent and energy dependent. So are you with me? So now we have applied a certain voltage, quite a high voltage. So therefore the minimum energy range in this source point and drain point is much different, and this reduction in our scale is corresponding to this energetic difference is corresponding to Q times VD. By applying certain drain voltage, we can pull down our minimum energy at drain side, and that is corresponding to this location, energetic location of this point. After that, we have just exponential decay of occupancy. Why? Because in many cases, if it is a Fermi-Dirac distribution, equilibrium distribution can be expected behavior just like exponential function. The tail of a Fermi-Dirac distribution function just looks like a Maxwell-Boltzmann distribution, and it is just exponential decaying. So now you can see that here, exponential. Please note that this is just a logarithmic scale. So this straight line is corresponding to exponential decay of occupancy. Simply speaking, if we go to higher energy states, then there is a much less probability to fill those states. So this is just Maxwell-Boltzmann distribution, and here we have also Maxwell-Boltzmann distribution, exponentially decaying. So nothing new and nothing interesting in this main part, but please have a look at the part shown here. I will introduce a little different color to highlight this part. So now you can see that. Can you see it clearly? So here, now we have a certain green lines much deviated from just a simple exponential decay. So please note that if this energy distribution at drain side really follows just Maxwell-Boltzmann distribution, then we can expect just a straight reduction of distribution function in this semi-logarithmic scale. But what is this? It means that in this device, when we apply high drain voltage at a certain energy range, in this energy range, we can expect more electrons whose kinetic energy is non-negligible. So because kinetic energy is just measured from this bottom energy, so this is corresponding to 0.3, 0.4, and it is almost corresponding to 1 eV and blah blah blah. So in this case, if this is nearly close to the equilibrium, then almost we have no electron at all. However, we have something like a 10 to the minus 6, so 10,000 times larger than its equilibrium distribution. So they are called as hot electrons. Why they are called as hot electrons? Because their kinetic energy is much higher than KBT thermal energy. Yes, they are really exceptional ones, and we can find many of them because the distribution function is highly deviated from the equilibrium distribution. Then you can ask me this question: why we have deviation from our equilibrium case? The answer is strikingly simple. So it's like this. We send our electrons from source side. So please have a look at an electron shown here. We send our electron. This is the injection point of our electrons. Of course, even in this energy scale, we inject electrons more frequently. And here we have injected electrons, and of course, even this extremely high energy, we inject electrons. But please note that in this case, most of our electrons are injected in this relatively low energy level, but it moves and eventually hit the wall, potential wall. Then what will happen? It just reflected and come back to the source. So nothing interesting happens for this guy. So let me just draw once again. If we inject our electron from source in this moderate energy range, then it goes and hit the wall and come back. So it cannot overcome this potential barrier. And now let's go to the energy level, which is slightly higher than the maximum energy of this potential barrier. Then what will happen? So let me just explain. So if this is energy scale and this seems to be the maximum energy of this potential profile, and if we inject our electrons in this case, then now it can have some chances to overcome the barrier and eventually go to the source drain end. If that is the case, if this electron can overcome the barrier perfectly, then what will happen? Then we will have just a straight line, horizontal line along this iso energy line. So we have much differences in this expected behavior and observed behavior. I mean that here we start from, for example, 10 to the minus 5, and if that is the same case, then we will have once again 10 to the minus 5. But you know, in this case we have a much lower value, 10 to the minus 6, 10 to the minus 7. So it means that although we have the open window for our electrons, but some of our electrons are experiencing certain amount of scattering event. So it is reflected and reflected during its journey. So that's the reason why our injection electron density distribution and the final endpoint distribution function can be different. So it means that if you insert or inject some electrons, then some of them are reflected and some of them are eventually arrive at the drain. And another one is, now you can see this wavy shape here. You can see that there is a certain amount of quite seemingly weird wavy shape, but when we measure the difference between this peak, the local peak, and another local peak, and the distance between this another peak and another peak, these are just given as a constant. So this waveforms or distribution function shows some oscillation, and their energy difference is the same. And this energy difference in silicon material is given as about 60 millivolt in this case. And please don't be confused with 60 millivolt per decade. This is nothing related with that subthreshold swing. This is this 60 milli electron volt energy. More exact value is 63, and that is corresponding, I don't remember exactly, 61 or 63, sorry, but this energy is related with most representative our phonon energy. Inside our silicon system, there are so many phonon modes to interact with electrons, but among them, the most efficient one, most active and most profound one is corresponding to the energy of 60 milli electron volt. So simply means that once our electrons overcome this energy barrier, then at certain position it can experience the interaction with the 60 milli electron volt phonon. So it loses its energy by amount of just 60 milli electron volt. Since its kinetic energy is so high, only once interacting with the phonons cannot entirely release its entire kinetic energy. So this means that the transition from this point to that position simply means that only small amount of 60 milli electron volt energy is transferred to phonon, and now it continue its motion, and also it lose its energy once, lose once, and lose once, and eventually approach to the sea of cold electrons. So are you with me? So let's say that you are going to the casino and you have a lot of money, and you wanted to just spend all of the money before coming back to, for example, Korea. So you are in USA or some other country where casino is not unlawful. So in this case, Now you have to spend your entire money. However, the seed money in your game is just restricted to, for example, 10 US dollar per game. Then you have 1,000 US dollar. What will happen? You have to lose 100 times to lose entire your money. Just similarly, now this electron becomes this one has a lot of kinetic energy, but it has a limited ability to release its energy. So in order to be cold enough, then it should interact with this representative phonons so many times, and that is shown here. This kind of information cannot be simply obtained from our, unfortunately, our current analysis tool, distributed diffusion model. This is beyond that. So for that purpose, we have to solve a more advanced transport model called as Boltzmann transport equation, or even higher one. But this is far beyond than our usual analysis model. So I will just explain what is the meaning of this energy distribution function. So if we can have energy distribution function from this information, what we can say is, in order to be eligible for impact ionization, its kinetic energy should be larger than 1.12 electron volts. So then where can we find some electrons which can initiate the impact ionization? So what we can say is, if that is the ground minimum energy, then maybe the energy beyond this part, they can initiate the impact ionization, and their distribution function is corresponding to just 10 to the minus 9, 10 to the minus 8, 10 to the minus 10. So it is really improbable to have any electron that energy range. So we call them as quite lucky, because most of electrons are having much lower energy, and only extremely small number of energies may have such a high energy. But once it has high enough energy, then it can now initiate impact ionization. We have seen our previous lecture. Okay, so that is one thing. And this kind of hot carrier effect. So then what happens to our hot carrier effect generated one? So I just told you that in the previous lecture. So if these electrons becomes hot, then it can introduce impact ionization, and additional electron hole pairs are generated, and they are working as the source of leakage current. So unwanted current can be generated by this impact ionization. This is undesirable one. But there is also another device which actually utilizes that effect. That is called as flash. Have you ever heard about flash device? So in this case, they intentionally use this kind of a mechanism. It means that once they apply high enough voltage, then make so many electrons which is hot enough, not just to 1.1, but seems to be its value should be about more than 2 eV or 2.5, even 3. If we have that kind of super excited electrons, then for those hot electrons, even the wall between this silicon and this gate, called as silicon dioxide, that can be regarded as a finite barrier. I mean that to me, just 1.7 meter tall. So actually Mountain Everest seems to be infinite wall. But however, think about a certain giant whose height is almost close to just half of it, like a super Godzilla. Then to it, actually Everest seems to be just a small wall, and if it tries to climb it, then maybe it can try to overcome this mountain Everest. So to me, it is impossible. So this silicon dioxide material, from the viewpoint of our normal electrons, this silicon dioxide electron should be regarded as infinite wall because its energy difference is more than 3 electron volts from the conduction band of silicon, so never can overcome that amount of energy difference. But now let's think about certain electron which is lucky enough. Now it becomes 2.5 eV or even 3 electron volts. Its kinetic energy becomes that amount. Then now the potential barrier given by silicon dioxide now becomes just accessible, and some of our hot electron can move into this conductive layer. So it means that if we have a hot electron and some of them can overcome the barrier and enter into this part, then we means that engineers intentionally introduce such a kind of structure. Here we have insulator, and here we have certain charge storage layer, and once again another insulator, and finally we have the rear gate. So now by applying high drain voltage at the same time high gate voltage, then now what will happen? Now these electrons becomes hot, and this gate voltage try to lower the potential barrier experienced by this hot electron. So by combining them, then we have a much higher probability for this electron enter into this storage node. So in this case, in this storage node, we can just take some electrons generated from this hot carrier mechanism. So this is one way to generate the flash memory, especially in terms of there are some variants of flash memory, and there is not NAND but no flash. In this case, they are utilizing hot carrier mechanism to write their information. Okay. So anyway, nowadays no flash is not much interested in mass production. Of course, we are mass producing the NAND flash, but if you are interested, for example, neuromorphic application in these days, then this no flash structure is more closely related to the structures suitable for neuromorphic applications, and they means that researchers are coming back to this no flash structure and try to make a certain innovation in this device structure. So simply speaking, if you wanted to do something special or something unusual, then you have to understand not only the main transport behavior or main characteristics of your system, but you have to understand additional features like hot electrons or impact ionization, many kind of generation recombination. Those are required. Okay, so now let's go to next slide. This is corresponding to a reliability problem. This is really long story, and actually there is a well-known international conference actually devoted to only this problem, reliability problem. So let me just describe first what it is. Once you fabricate your chip, then you sell it to your customers. Then there is a certain guarantee that your device or your chip performs, for example, 10 years. So if you use it in a normal operation condition, then you should allow most of your chips are surviving after 10 years. So if that fails, so of course, if you just release so many chips, then some of them eventually fail. Then customers do not complain about the reasonable number of failure. They know the electronics, so they do not complain. But what happens once you buy your chip, and after just several months later, your customers start to complain. Something happens. My chip works perfectly, but after some months, then they are gone. So malfunction. Then what will happen? There will be the lawsuit between your company and customers. So that introduces a lot of problems to the company. So when we sell a certain chip, then we have the guarantee about not just for initial performance, but its wearing characteristics. After 10 years, we should guarantee it is working. That is related with reliability problem. So simply speaking, so usually the guarantee is usually done in 10 years. Of course, it depends on the case, but anyway, this is the one. And depending on the fields, the degree of this guarantee is somewhat different. One of the most serious one, the most strict one, in our case, in our normal application, would be automotive applications. If you buy your chip, insert it to your car, then it should survive 10 years. So during driving, certainly your chip goes away and an accident happens. Then who should be liable for that amount of damage done by this electronics? So automotive one is quite strict. However, we have even more strict one. So please guess. Even more strict one is space application. So if you send your chip into the space, then say that some of them is gone, because the environment is really harsh, because now our chip is no longer covered by our air, which can protect many of rays from rays. Then now it is just exposed to so many energetic components from the external world. So, and it is really mission critical. If you fail, then so the damage you have or the loss you have cannot be measured easily. So therefore, there are many different cases. But also there is, if you go to consumer electronics, actually the amount of reliability is not that significant. For example, you buy a USB stick at a store, then you use it, then some of your USB drive is gone, so you lose your memory. You get very angry. However, the amount of you can return from your chip company, it would be quite small, because the information you have is not that in this scale, not that important. And so we have, in the case of NAND flash, we have tons of spaces. so we can just move one information to the other, and we have many copies, and the real occurrence of that difficulty or that problem is quite rare. So anyway, this reliability is quite important in practice, and actually this is the point of most alternative technologies fail. Because if you are developing new technology, so you have made a fantastic device, but usually that fantastic device with fantastic materials are not strong enough compared with the silicon. So that's the reason why, although I made a fantastic device, but after a few days later, its characteristics, IB characteristics, just degraded by some oxidation or exposure to the air. So as a mass production point of view, this reliability is extremely important. Actually, if your technology cannot pass this reliability test, then nothing happens, just meaningless and useless one. So please, I'm not discouraging you to work about new technology. We have to investigate quite seriously about the new technology. But please keep in mind, writing just a good paper with new technology and making it to eventually to the mass production, there is a huge differences, and don't expect it too early. But new technology itself has its own value, and only few of them can be realized. But once it becomes realized, then that will change the world. Okay, so actually, who knows? Nobody knows that my technology will be the winner. But anyway, if everybody do not try to develop a new technology, then nothing will happen. Our industry will just keep this state of the art. So anyway, we have to try, but please note that in mass production, we have a serious war of this reliability. So reliability is a matter of 10 years guarantee. So company cannot do this job. Once develop a technology and test their chip 10 years, once after 10 years has passed, oh, my chip has survived, then I start to sell it. So it never happens. Once your device is fabricated, as soon as possible, you have to deliver it, release it to your market to dominate the market. So there is some contradiction. You have to wait for a while to check the reliability. However, you cannot wait for a long time to test reliability. So what we do is, here we introduce this elevated temperature test. It is known that if you elevate the temperature, then this kind of reliability problems becomes exaggerated. So it becomes more severe than the one at room temperature. So that's the reason why when we try to test the reliability problem, we intentionally increase the temperature and just test it several just days, and say that at this elevated temperature, several days is corresponding to at room temperature 1 year or 10 years. That is the typical way we test our chips. So you know that in this case we are just believing that it works. So therefore these guys, the reliability guys, becomes extremely conservative. So because anyway, they should allow our company to start the mass production, and once after mass production start and several months later certain problem occurs, then who is reliable? So this reliable guy should take that reliability. So therefore they become extremely conservative. So that is quite a tough job. And here we have two different devices called as P MOSFET and N MOSFET. Usually they are drawn in this way, and this is corresponding to the P MOSFET, and its bias is corresponding to the VDD. So its source is connected to VDD, and it's here we have N MOSFET, and here we have its source is ground connected to the ground, and either we can apply 0 or VDD to our this logic system. So let me just consider two cases. Once, so we apply logical 0 to our input value. Then what will happen? Our N MOSFET is actually turned off. So because we have 0 VGS value, so this one becomes just off. Instead, now we have just to have minus VDD difference in its P MOSFET VGS value. So this one becomes just on. We have a lot of holes beneath of this position. Then now what happened? This one becomes extremely low resistive, and this one becomes extremely highly resistive. So most of voltage between ground and VDD should be applied to only this NMOS part. So simply speaking, we know that the output becomes just VDD. So we have two different resistive components, and who takes the entire voltage drop? Resistive one takes all. So that's the reason why entire VDD is applied to this NMOS part. So please have a look at the condition of our P MOSFET and N MOSFET. From the viewpoint of a P MOSFET, how large is its VDS value? What is the voltage difference between source voltage and drain voltage? It is almost exactly 0. And how about the VGS value, gate to source voltage? It becomes minus VDD value. High negative value is applied to our P MOSFET. But please consider this N MOSFET. In this case, how large is its VGS value? It becomes just 0. And VDS, that becomes VDD. Okay, so are you with me? So in this case, from the viewpoint of P MOSFET, it experiences certain cases like this. I have almost no difference between source voltage and drain voltage, and instead my gate voltage is biased to the 0, so my VGS becomes minus VDD, highly turned on P MOSFET. It is well known that if we have highly turned P MOSFET, and so this is corresponding to the B of BTI. This is corresponding to the B of BTI. We apply high voltage to our P MOSFET. Temperature, okay, we introduce high temperature. If we apply high temperature and high bias to our P MOSFET, then it is known that threshold voltage is changing quite rapidly. Of course, rapidly means that it really everything is relative. So what is the rapid or not? But um, simply speaking, here means that if we apply high enough gate bias, absolute value, and at elevated temperature, then instability means that instability of our threshold voltage. Threshold voltage, when we make a fresh device, then it had certain threshold voltage. But if we apply high temperature and high bias, then now its threshold voltage drives, and after 1 year later, we have a different device whose threshold voltage is much different from previous case. That is the bias temperature instability, and this one is typically very serious for our P MOSFET. When we have a P MOSFET and when we apply negative bias, then it becomes really significant. So maybe later, if you go to the industry, then maybe you will hear about NBTI. So BTI in general means that bias temperature instability, but N means that now you apply negative gate voltage to your transistor. So for your P MOSFET, MBTI becomes a quite significant reliability problem. So you don't want to have it. So what we do is just to test, for example, in this case, at elevated temperature with 1000 seconds. 1000 seconds means that just 16 minutes, and they test this device, and by applying here OV means that overdrive voltage, the voltage beyond the threshold voltage. If in our case, for example, this is if that is P MOSFET, it means that actually you apply the VGS value like VT of your P MOSFET minus 0.7 volt. So when you apply such a low gate voltage, then now only 16 minutes later, your device shows about 6 millivolt difference in its threshold voltage. Well, 6 millivolt is not that high, but you know that if we project it into the room temperature, so then that is corresponding to, if we go to 10 years, that this is corresponding to 50 millivolt. So which is almost the border of our reliability problem. So 50 millivolt is corresponding to 0.05 volt, but you know we have to guarantee that even though we use it 10 years, our threshold voltage does not vary that much. That is the amount of we have to guarantee to our customers. So okay, so finally for this part, the first part of our today's lecture, we will talk about breakdown. But I think that this one has been already, the main mechanism already has been considered. So impact ionization. Have you heard about impact ionization in our previous course? Yes. Even today, I told you that when we have hot electrons, whose kinetic energy is even larger than band gap energy, then it can contribute its excessive kinetic energy to the silicon structure, and one of our valence band electron can jump into the conduction band. That is a secondary electron hole pair. So, you know, this impact ionization was initiated by this hot electron, and this guy was the main cause of high substrate current of our MOSFET. However, that was just a liquid current, and this breakdown means that when we apply even higher voltage, something happens. It means that so usually here we have a ball. Then if we just release it and it experience free fall, and let's say that when it free fall, then yes, it goes. Then once again it goes to free fall and it bounce once again. So eventually, if there is nothing happens, so if there is no bouncing effect, then after a few times later, it will eventually stop at the ground. This is the case we have just a normal, some reasonable value of drain voltage. But the case we are currently considering is even serious. So now we started from 1 electron. Well, then now it becomes hot. So it generates 1 electron hole pairs. Now it becomes primary electrons, secondary electrons, and secondary hole. Then these two primary electron and secondary electrons are moving. And since electric field is so high, even this secondary electron and the primary electron, which was previously hot, but that now it becomes cold, but it becomes once again hot. So it generated once again electron, hole, electron, hole. This guy is primary, and this guy is previously secondary electron, but now it becomes a primary one, and secondary one is generated. Simply speaking, if we apply sufficiently high drain voltage, then secondary electron can work as a primary electron, so it can introduce a lot of electrons after a few steps of this chain reaction. Of course, you should ask this question. Yes, once this electron becomes hot, this is quite a rare case. We have the small probability of having hot carrier. So now we have electrons. Although we have 2 electrons, and not 100% of them becomes hot. So there is also small chances for our electrons become hot. So simply speaking, you can think about 2 competing mechanisms. When you apply high drain bias, then we are now increasing the occurrence of hot electrons. Many more chances to have hot electrons. But also same time, this hot electron generation becomes a quite a rare case. So you have to have 2 competing behavior. So eventually, when you apply extremely high drain voltage, then now becomes this chain reaction overcome certain boundary, and now this one becomes self explosive. So there becomes so many electrons generated from this one single primary electron. If we have that case, once we inject one single hot electron, then that will generate a lot of a set of generated electrons, and that will introduce sharp increase of our drain current. So simply speaking, if we increase drain voltage, then of course there was a certain amount of current level which is quite meaningful. So this is the usual way we use the transistor. However, if we have a certain voltage, usually called as breakdown voltage, if we exceed that voltage, then suddenly this transistor conduct a lot of current, several thousand times higher current than its usual operation condition. So you cannot use it for your nominal operation. It is a critical problem when you use it for your power device application. For example, although we are mainly talk about the logic device which make a VLSI, but even in this VLSI circuit, there is the logic central part, and they should be supported by so-called I/O devices, so input-output devices. They should work with not 0.7 volt, but they should work with, for example, 3.3 volt or 5 volt or even higher voltage is required to biasing them. So for that purpose, we need some somewhat more strong devices. So it means that in the world of our chips, yes, there are smart guys. They can do many kind of computation, but they are quite weak. If we apply certain small high voltage, then they becomes just gone. So we should provide them. And however, external world does not work with just 0.7 volt. We need much higher voltage to activate the external physical world. So for that purpose, we introduce certain guys called as I/O devices whose operation voltage is much higher than this logic central part, and these guys are working in a higher voltage. This is one way we have higher drain voltage. Another one is really power device. In this case, for example, when we generate electricity, then we have, for example, voltage range of kilovolt range or megavolt range. That amount of voltage is generated, and who can deal with this extremely high voltage? So actually, that should be also controlled by our semiconductor devices. And who can generate it? Yes, actually, some companies should fabricate certain power devices. So in that case, our transistor should operate quite normal even when we apply kilovolt to its drain side. Then we need to have extremely high breakdown voltage. Behind or below this breakdown voltage, our transistor work as just a normal transistor, and beyond that, it stops its normal working and just conduct a lot of current, and eventually it mechanically damaged because it conducts so many currents, so high current, it generates a lot of heat, and that actually demolishes the crystal structure of our silicon devices. So this is the breakdown. But in many cases, when we use just a CMOS circuit, especially at the center point where logical operation occurs, usually our operation voltage is much lower than breakdown voltage. So this is not for logic device, but for I/O or power devices. Okay, now we have just 13 minutes left, but now let's start our uh, double gate discussion. Up to now, we have thought about a planar MOSFET. So planar MOSFET about 15 years ago, we means that the industry have made transition from planar MOSFET to the multi-gate MOSFET. So we are living within the era of multi-gate MOSFET. Although we have spent quite a lot of time for talking about the planar MOSFET, but planar MOSFET is not for the state-of-the-art devices. If you are working with the state-of-the-art devices, then you have to consider so-called multi-gate MOSFETs. So from now on, I will talk about their properties. Here we have one figure taken from Professor Tower's textbook, and now it says many things to us. So let's have a look at it. So this double gate means that we have two gates. So when it was first proposed several decades ago, actually people have thought about this case or double gate. Yes, we have gate 1 and gate 2, and maybe we can independently control these two gates to get maximum ability to extend or improve its performance. But nowadays there is almost no independent gate control of this double gate. So although physically they are double gates, there are two gates, but they are biased at the single gate voltage. Simply speaking, here we have a silicon, and here we have a gate, one top gate, and for example bottom gate, and almost entirely we apply the same voltage to this top and bottom. So they are called as common operation, and we are talking about common gate operation. Actually, even physically, they are actually merged into one part. Here you can see three different possibility having double gate MOSFET. Although it is written shown in our textbook, but it was initially published in a research paper by other author, but I just took it from the textbook. And here we have three different possibilities to have channel direction. Please note that this direction, this plane, is our vapor plane, and in this case this plane is vapor plane, and this one is also vapor plane. So simply speaking, in this case A, now our channel just placed horizontally. I mean that we have a paper of a sheet of paper, and if this is vapor, then we are placing our channel in this way. Just in plane transport occurs. So where can you find this kind of a double gate MOSFET? This MOSFET, this in plane transport vapor corresponding to the vapor surface, this is corresponding to nowadays state-of-the-art device, nanosheet transistors. In the case of nanosheet transistors, we are placing multiple sheet of silicon layers, 1, 2, 3 in parallel. So simply speaking, here we have one sheet, and on top of it we have another sheet and the third one, and we place, for example, here source and here drain. This is the form of state-of-the-art logic device. And let's go to the case B. In the case of case B, where can you find this kind of thing? In this case, this is the direction. The current flows vertically or perpendicularly to the vapor normal surface. Vapors, so this is a vertical transport. And actually, in the logic case, it is difficult to find it. But you know, quite interestingly, in this year, many companies are demonstrating that their new DRAM architecture. In their new DRAM architecture, they are adopting this kind of structure. Their transistors are placed certain source and drain, and current is flowing in this vertical way. Why they do that? Because here, once they fabricate their device in this way, then they just introduce certain capacitor. So now here we have one transistor, and on top of this one transistor we place one capacitor. You know, since you are Korean, so maybe you are quite familiar with DRAM, and this DRAM typically has the architecture of one transistor and one capacitor, and always this capacitor takes a lot of area for our DRAM technology. But if we adopt this kind of vertically placed transistor, and if we place it on top of it, then we can really minimize its energy area consumption. In the case of DRAM case, the most important one is actually its size, its area consumption. So by adopting this new technology called as 4F square DRAM, so now we expect that we can reduce the area quite significantly for a while. So nobody think that this will be the ultimate form of DRAM, but as an intermediate remedy for this challenge for further reduction of scaling, we feel that this one becomes for a while the form of a DRAM transistor. And let's go to the final one, C. In this case, our channel is our current conduction is still in plane, but now this vertically placed sheet is corresponding to the channel shape. Here we have source, and here we have a drain, and we have a tall structure called as a fin, and this one is this typical structure C is called as a fin FET. So actually in lecture 20 I have shown how can we fabricate a fin, actually a set of fins, by doing certain kind of fabrication steps. So maybe you remember that after all kinds of complicated etch depot, finally we generate parallelly placed structures, and each of them are called as a fin. And by placing gate, source and drain to that fin, transistor becomes a FinFET. That was the mainstream logic device down to N3 node, so corresponding to a 3 nanometer node for TSMC. And in the case of Samsung, they transit a little bit earlier. They start their last FinFET node was their 4 nanometer node. But anyway, so that was from starting from 2000, I don't know, maybe 2010, about 2020 something, I mean that 23, 4. So during that time, FinFET was actually the transistor. And now nanosheet is now the transistor, the state of the art transistor, and this is case B is corresponding to the 4F square DRAM. And yes, so now let's go to a little bit more about it. So up to now I have discussed about double gate MOSFET, but actually what we really use is not exactly double gate, but so-called multi-gate. Multi-gate means that 2, 3, 4 or something. So we have many gates. Actually, so don't be fooled by this multi. There is no separated 2 gates or 3 gates. They are all connected. But for example, when we have a certain silicon, and let's assume that this is just a rectangle like, then if 2 faces are covered by gates, then we say that okay, there are 2 gates, so this is called a double gate. And if 3 faces are covered by gate, although they are in one body, but we do not call it as a single gate, but we call it as 3 gates. It sounds a little bit complicated. So we have only one single gate, but this single gate covers 3 faces of our cross section. And if we cover all of them, then maybe we can say 4 gates transistor, but usually instead of this 4 gates, we call it as just GAA, gate all around transistor. So that is this is just historical naming, so don't be fooled by this strange naming convention. But anyway, nowadays all of our state-of-the-art devices are in the form of multi-gate transistors. So let me just emphasize once again, FinFET. Yes, this one has here. When you have a look at this one is a fin. And actually, where can you find the gate? You can find the gate here, there, and there. These are gates, and we feel that this is corresponding to 3, 1, and gate all around 1. So I will explain it later. And okay, here you can see that this one is a silicon. This blue guy is a silicon, and it is covered by gate. Also, this is silicon, and this is covered by gate. So we say that this is corresponding to the gate all around the transistor. And this is NAND flash memory, and you can see that there is this one is corresponding to the silicon, and inside it we have actually silicon dioxide. So this is usually called as a macaroni structure. So pasta, one of your favorite pasta, macaroni, it has an empty space, and only silicon covers just the outer space of this circle, and it is covered by this gate. So this is also gate all around the transistor. Finally, DRAM. So although I have shown you that 4F square DRAM, this is really double gate, and eventually we will move to 3D DRAM, and 3D DRAM is also in form of a multi-gate transistor. So simply speaking, although we spend almost 2/3 of our lecture hours semester to the planar MOSFET, but nowadays state-of-the-art devices are all multi-gated devices. So we have to study the multi-gated devices. So that is the main point of today's talk. And yes, from next one, we will dive into very complicated formulation for double gate MOSFET. Thank you.